what we'd like to share with you today, that we now have full confidence that there is methane occasionally present in the atmosphere of Mars, and that there are organics preserved in ancient rocks on Mars in certain places. This is important. Methane in the atmosphere and organics in ancient rocks are important because they are chemically reduced molecules. On terrestrial planets, they compete for destruction with other kinds of molecules that are more oxidizing. And their preservation and occurrence is a certain matter of luck, for which science must provide a search paradigm in order to better understand how these materials are produced and where they go. But most importantly, they can both be consistent with the former presence of life, or the existing presence of life.
This was an ancient environment with the right elements, minerals indicating a near neutral environment, and slightly salty liquid water. All the prerequisites to support life, a habitable environment.
I think we have found a habitable environment that is so benign and supportive of life that probably if this water was around and you had been on the planet, you would have been able to drink it.
So, although at this point in the mission we can't conclude that there was definitively life on Mars, the SAM discoveries have really shown us that all of the basic ingredients for life were there, including complex organic compounds, the building blocks of life. Now, with the detection of organics in Gale Crater, the probability that Gale Crater Lake could have supported life goes up.
Mars is very Earth-like, or at least used to be very Earth-like. It is a planet, sister planet to Earth. It is the most likely planet in our solar system that had life at one time, may have life now, and we feel definitely can sustain life. So that's the reason we chose it. It's definitely one about survival of the species, if you will. You know, the more we can expand humanity across the solar system, the more we're going to understand about our own Earth.
The Knocklift Plateau, it studied fractures in the ancient sandstone where groundwater once flowed and permeated the surrounding rock, causing changes in chemistry that created light-toned halos around the fractures. The science team compared rock powder drilled from the halo with that drilled from unaltered rock. The haloed regions were enriched in silica but depleted in other chemical elements. It appears that groundwater transported chemical elements from some rock layers and deposited them in others.
Now, data from MAVEN are supporting this model of solar wind erosion. This graph shows the first ever measurements of oxygen ion flux around Mars, allowing us to see the solar wind driving the atmosphere into space in both the polar plume and the tail regions.
By comparing gravity with topography, the scientists made an improved estimate for the crustal thickness of Mars, shedding light on its geologic history and confirming earlier indications that the planet has a molten outer core. The orbital data also revealed seasonal variations in the mass of the polar caps, showing that up to 4 trillion tons of carbon dioxide cycle annually between the poles. The new gravity map should prove useful to future missions as well, by allowing spacecraft to enter orbit more precisely, thus ensuring that the Mars fleet continues to return a massive trove of data.